Hello once again, math contest enthusiasts. We're going to continue on our examination of the 2014 Fryer contest. That's the grade 9 level contest. We're on to question number 2, so let's take a look. Alright, looks like we have some triangles, and it's another 4-part question just like the last one. So A part, where we just need a final answer. In triangle ABC, the angle at B is going to be 60 and the angle at C is going to be 50. What is the measure of angle BAC? Okay. So I think it's still covered in the 9th grade curriculum, but it bears writing down. So the sum of the interior angles of a triangle is 180 degrees. So we know the other two angles, ABC, and we know ACB, and we're asked for BAC. So that's 60 degrees, 50 degrees, BAC. And that means BAC is going to be 180 degrees minus 60 degrees minus 50 degrees. Well, that's just 180 degrees minus 111 degrees. That's going to be 70 degrees. And that should be our final answer. Exactly. Okay, so simple enough starter question, that's all right, but I'm guessing that we're going to be talking a lot about angles, or they wouldn't have given us such an easy A part. That was probably worth 1 mark. I don't think it'd be worth 2, but maybe. Okay, B. An angle bisector, for those of us who don't know, is a line segment that divides an angle into 2 equal angles. So, an angle bisector of this 50 would be a line going through C, and it would have an angle of 25 on the one side and 25 on the other side. That's what it means. If we were to bisect the angle of 60 degrees, we'd get 30 on one side, 30 on the other. Just splits the angle in half, that's all it is. In triangle ABC, once again we have the angle at B is 60 and the angle at C is 50. If BD and CD are angle bisectors of ABC and angle ACB, respectively, what is the measure of angle BDC? Okay, so we're asked this angle right here, this smaller angle. We know we got 60 here, we know we have 50 here. If we need to from part A, we have 70 up here. And we know that these two lines split these angles, the 60 and the 50, in half. So how about we just reproduce our picture to start off with? Doesn't have to be exact, it's only for our purposes of marking things down and exploring the angles. Now, since BD bisects the angle ABC, then the angle on both sides is going to be a half of 60. So DBC is going to be 1/2 of angle ABC, and that'll be 30 degrees. So we have 30 degrees here, we also get a 30 degrees up here. And likewise on this side, we're going to split this angle of 50, we'll get 25 degrees and 25 degrees. And in this way, we're going to be able to use the exact same method we did in the previous question. The sum of the interior angles are 180 degrees, and so that should give us the angle BDC. So we know 180 degrees is the sum of DBC, BDC, that's the one we want, and DCB. Or I'd probably write that BCD, but doesn't really matter. So that's 30 degrees plus the one we want to figure out, plus 25 degrees. So BDC is 180 degrees minus 30 degrees minus 25 degrees, or 180 degrees minus 55. So 125 degrees. Okay. So that's B part, another final answer style question. That's okay. Now let's take a look at C, a written question. Point S is inside PQR, triangle PQR, so that QS and RS are angle bisectors, okay, just like we had in the previous question. And QS is equal to RS. So these two lengths, as we have denoted in the diagram for us, these lengths are equal. Okay. If angle QSR is 140 degrees, determine, with justification, the measure of angle QPR. QPR, so this big one up here. Okay. So we know this angle, and we know that we have a small isosceles triangle here. Well, in isosceles triangles, the angles opposite of the equal sides are themselves equal. So we have 140 here, and we know these two angles are the same. And then we know that these are the bisectors, so we'll be able to duplicate that angle, get these two angles, PQR and PRQ, and from there we should be able to work out the angle of QPR. So I'll show you what I mean. We draw ourselves a little picture. We have P, we have Q, we have R, and up here we have S. And we know we have 140 degrees here. Now, since triangle QRS is isosceles, then we can let x equal SQR, and that'll be the same as SRQ. Both these angles are the same, and they're x. Okay. We know 180 degrees is going to be angle QSR, which is the one we know, plus SQR, which is x, plus SRQ, which is also x. So that's 140 degrees plus 2x. So x is going to be 180 degrees minus 140 degrees over 2. So that's 40 degrees over 2, so that's going to be 20 degrees. Now we know QS and RS, in addition to being equal in length, they're also angle bisectors. So they bisect angles PQR and PRQ, respectively. So that means that to find angle PQR, we would double angle SQR. That's going to be 40 degrees, and likewise, PRQ is going to be double angle SRQ. But this is also 20 degrees, so twice 20 degrees is again 40 degrees. And then we know 180 degrees is going to be angle PQR plus angle PRQ. Plus the angle that we were asked for, QPR. (40 degrees plus 40 degrees plus angle QPR. So we can rearrange this. And we get 100 degrees. And that gives us the value of angle QPR. Okay, that sounds fantastic. And that's all we were asked for C part. That's great. And we justified it by stating what we were doing as we went along. We mentioned that we can use the isosceles triangle to figure out these two equal angles here and here. Then we use the bisecting angle, the angle bisector knowledge to double those angles, and a simple interior of the triangle being the sum of 180 degrees got us the final answer, the final angle that we want. Okay. D. In triangle PQR, QS and RS are angle bisectors of PQR and PRQ, just as before. And we're also having QS is equal to RS, just as before in this diagram. Explain why it is not possible that QSR equals 80 degrees. Okay. Well, let's suppose it were. And we'll see if we can work out some sort of contradiction, like maybe these two lengths can't possibly be equal, or maybe one of these triangles isn't really a triangle. Who knows? Well, let's take a look. We have the exact same diagram, but I think I'll just get a new page and redraw it, just because so suppose angle QSR equals 80 degrees. So we're going to assume that it is 80 degrees, and then see if we can get this to show us some sort of nonsense statement. And if we get a nonsense statement, we know that our original assumption, because we only made this one, our assumption that 80 degrees was the measure of QSR, that had to be false. You know, it's garbage in, garbage out. You make a crazy, stupid assumption like 2 equals 3, of course you're going to be able to get absolute nonsense like all circles are squares, things like that. That's called a proof by contradiction. So we get 80 degrees in here. SPQR. So let X be these angles here. SQR and SRQ. It hasn't changed the fact that this is an isosceles triangle. So I'm guessing that maybe PQR would have to be 0 or something. That would be a sort of nonsense answer. You can't have a triangle and one of the vertex angles is 0 degrees, or you can't have it be 180 degrees or something like that. That's the sort of nonsense answer that we might be looking for. And why might we be looking for this angle being absolute rubbish, a complete nonsense answer, something that doesn't make any sort of logical sense. The reason we might be trying to look for that angle is because that's what we had in part C. C and D are very similar setups. You know, we draw basically the exact same diagram, just a different angle. So in the last one, they had us figure out this angle, so maybe they're hinting at, you know, try and explore and get to that angle. Okay. So once again, x is going to be 180 degrees minus this interior angle over 2. So that's going to be 100 over 2, so that's going to be 50 degrees. So just as before, we can figure out angle PQR. It's going to be twice x, so that's going to be 100 degrees. And angle PRQ, so that's going to be 2x, and that'll be 100 degrees. And there we probably have our problem. We have two obtuse angles in our triangle. You can't have two obtuse angles. We can go a step further and get ourselves a nonsense answer for this angle. So that gives us negative 20 degrees for that angle. Now, a triangle can't have a negative angle as one of its interior vertices. That wouldn't make any sense. Think about how we used to measure angles on a triangle. You get out your protractor. Your protractor goes from 0 to 180. You can't have a negative 20 anywhere. And that's sort of the reasoning behind this. You can't have a negative angle. So assuming we had an angle of 80 degrees led us to this ridiculous conclusion. So the only thing that could be wrong, I mean, the math certainly isn't. Math is straightforward. Math is logical. The only thing that can be wrong is our assumption of 80 degrees. We just assumed it. We had no motivation there. The question asked us to show that this can't happen. So we said, well, let's assume the opposite. Let's assume we do get 80 degrees. If we get a nonsense answer, our assumption must be wrong. So we can't have this angle be 80 degrees. Okay, and we've shown why. Proof by contradiction. Okay, we assumed it. We got a logical problem. We got something that shouldn't be true. It is something that's false. So that contradicts our assumption. Okay, and that gives us question number 2 on the 2014 Fryer. So, not a whole lot else to say here. Proof by contradiction, very important. It pops up from time to time on these Tron tests. It's a nice thing to know for these written style questions. And I think that's about it. So join me in the next video for question number 3, which looks like it also might involve some geometry. But I'll see you guys then.